Today we will be talking about the derivative. We're going to apply our knowledge of limits to figuring out how to calculate derivatives and find more information about the graph of a function. So the picture is going to be the graph of a function. Let's say this is my function, and here I've got the point x comma f of x. So apparently this is the graph of the function f, and over here I got the point x plus h comma f at x plus h. And what we do is we zoom in on this part of the graph, and in particular we get this part where here we have x comma fx, and here we have x plus h comma f at x plus h. And then what we can do is make a triangle like this, and the coordinates of that third vertex of the triangle will have to be x plus h comma f of x. You think about it, that x plus h is because it needs to have the same first coordinate as that point, and that f of x is because it needs to have the same second coordinate as that point. Now we calculate the slope of that line. The slope is equal to f at x plus h minus f at x. And that's because if you look at that right triangle, then the vertical line of that is passing through the point x plus h, fx plus h, and x plus h fx. And the difference between the y coordinates there is fx plus h minus fx. We're going to divide by the difference in the x coordinates, and that is h. So the slope is fx plus h minus fx divided by h. If you make that triangle smaller, then it's like you're moving the point x plus h, fx plus h over the graph to the point x comma fx. So move x plus h comma fx plus h over the graph towards the point x comma fx. What you see is that that triangle is then changing. Well, that triangle is getting smaller, and its top vertex is being pushed over the graph towards the left bottom vertex. So I can look at what happens with that slope of that changing third vertex, and then I get that fx plus h minus fx divided by h becomes a function of h. As the triangle gets smaller, h is going to go to 0 and vice versa. That means that the limit as h approaches 0 of that quotient is an interesting thing to look at. So we look at this limit, and then we're going to do some calculations with specific functions. So as I said, that function that sends h to f at x plus h minus fx divided by h is looking at that triangle that's getting smaller if I let h go to 0. We will say that f is differentiable at x if the limit as h approaches 0 of f at x plus h minus f at x divided by h exists. We call that limit if it exists f prime at x, and that number f prime x is then the slope of the tangent line at the graph of the function at the point x, comma fx. That actually means if I would do this for the point A rather than the point x, so if we do this at A, comma fa rather than x, comma fx, then the slope of the tangent line if f is differentiable at A is called f prime at A, and the tangent line itself has the equation y equals f prime at A times x, because the slope of that tangent line needs to be equal to f prime A. And if you calculate what that constant has to be, the constant of the equation y is the slope times x plus a constant, then that constant is going to be f at A minus f prime at A times A. Now we're going to do examples. f x is x to the power n. Want to calculate the derivative at a. So I want to figure out whether f prime a does exist. Now I happen to know that it is differentiable, so I'm just already writing it as an equality. It's the limit as h goes to 0 of f at a plus h minus f at a divided by h, which is equal to the limit as h goes to 0 of a plus h to the power n minus a to the n divided by h, which is equal to the limit as n goes to infinity, as h goes to 0 of, and then we get the binomial expansion a to the n plus n times a to the n minus 1 times h plus dot 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 plus h to the n minus a to the n divided by h. And that is equal to the limit as h goes to 0 of the a to the n cancels out of that. I'm going to look at the second term of the numerator, divide that one by h. That means I get n times a to the n minus 1. And then I'm going to write the rest as h stuff, and I still have to divide that by h. So I can say where h stuff is a sum of terms each of which has a factor h to a power of at least 2. And from that you see that if you divide each of those terms by h, and each of the terms has a factor h to a power at least 2, if you divide by h, then there will still be at least one h left, and as h goes to 0, that means that that limit as h goes to 0 of n times a to the n minus 1 plus h stuff divided by h really is equal to n times a to the n minus 1. Now, exercise. Write it out without h stuff. For n is 3 and n is 4. That means for f of x is x cubed and g of x is x to the 4. So we have now a nice supply of differentiable functions. Now I want to show a function that's not differentiable. So a non-differentiable function. That's not all that hard. The function f of x is the absolute value of x is not differentiable at 0. Why? Well, because if you look at f at 0 plus h minus f at 0 divided by h, then that is the same as the absolute value of h divided by h, and the absolute value of h divided by h is equal to 1 if h is positive, and it's equal to minus 1 if h is negative. So the limit as h goes to 0 of f at 0 plus h minus f at 0 divided by h does not exist. Other example. If I take f of x is the square root of the absolute value of x for all x in R, then I can observe that the f at h minus f at 0 divided by h is the same as, well, when h is positive, that's just equal to the square root of h divided by h, which is equal to 1 over the square root of h. That's if h is positive. And it's equal to the square root of negative h, because that absolute value of minus h is equal to negative h if h is negative. And I have to divide that also by h, and that is the same as, well, that denominator, if h is negative, I can write that as minus the square root of minus h times the square root of minus h. If h is negative, then minus h is positive, so I can take those square roots over here, and their product really is the square root of h. But if h is negative, then this product is negative h, but I want to have an h, so that's why I put that extra minus sign over there. And at the top, I'm now having minus the square root of minus h. So all of that, of course, is the same as minus 1 divided by the square root of minus h. And as h goes to 0, that limit does not exist. In a more dramatic way than in the previous example, because it does not exist for two reasons. First of all, that square root in the denominator is going to get small, and therefore the quotient is going to be large. And also, I have that behavior on both sides. Okay, now a little bit of theory. Differentiability is stronger than continuity. We've been talking a lot about continuity and not so much yet about differentiability. So what I mean is that if a function is differentiable, then it is continuous. Like, let's make that a theorem. If f is differentiable at a, then f is continuous at a. And when I talk about differentiability, just like when I'm talking about continuity, I'm assuming that I investigate that at a point where there is an interval around that point, so that there is space on both sides of that point to take that limit which defines the derivative. Okay, let's do the proof. The limit as h approaches 0 of f at a plus h minus f at a, and you're going to ask, why are you looking at that? Well, I'm looking at that because if h is continuous, then f at a plus h should be close to f at a when h is close to 0. That means that that limit that I'm writing down here should be equal to 0. Now, is it? Let me see. It's the limit as h approaches 0 of f at a plus h minus f at a divided by h, and then I multiply by h. And now recognize that first part over here as when h goes to 0, then that will go to the derivative. And I can apply the product rule for limits. That's the same as the limit h goes to 0 of f at a plus h minus f at a divided by h. And I'm multiplying that by the limit as h approaches 0 of h. And that first limit is equal to the derivative of f at a. And that second limit is equal to 0. So I get f prime a times 0, and that's equal to 0. Where in my argument I used that the function is differentiable. So if the function is differentiable, then I'm going to get that the limit of fa plus h minus fa is equal to 0. I claim, but then the limit as x goes to a of f of x is f of a. Now let's write that part of the proof out. How does a proof of that nature go? It goes by let epsilon be bigger than 0. Now, what I have is that the limit f as h goes to 0 of f at a plus h minus f at a is equal to 0. I'm going to use that now. So I'm going to choose my delta such that for all h in absolute value less than delta, we have f at a plus h minus f at a in absolute value is less than epsilon. That is just the definition of the limit as h approaches 0 of f at a plus h minus f at a is equal to 0. Okay, thus, for all x such that x minus a is less than delta, we have, let me write the reason for that. We have You're going to say, why are you writing that down? You'll see in a moment. We have, since x minus a, since a minus delta is less than x less than a plus delta, because that's what it means for x minus a in absolute value to be less than delta. We have, that's correct, and then also that means that minus delta is less than x minus a, which is less than positive delta. So then we get what? Well, my x minus a apparently is one of those h's. So I get that the f at a plus such an h as x minus a is minus the f at a in absolute value is the same as f at x minus f at a in absolute value. And remember, we already know that that has to be less than epsilon, so that is less than epsilon. Notice that the proof has the standard format. I had to prove that this limit x approaches a of f of x f of a. I said 1, let epsilon be bigger than 0. 2, I chose a delta. And then 3, if x is such that x minus a is less than delta, then fx minus fa is less than epsilon. So that completes our proof. What did we prove? If f is differentiable at a point, then it's continuous at that point. Other way around, not true. And once again, not f is continuous, then f is differentiable. Example we saw above. Example would be the absolute value of x. Here's the x-axis, here's the y-axis, and here's f of x is the absolute value of x. It's not differentiable at the origin, right there. It's not differentiable there. Bad point. But the function is continuous at 0. Now you can make that worse. So just to sketch that, the book has a much better sketch. You could start with 2 of these triangles and say, well, clearly that function is not differentiable at that point for the same reason as why that one is not differentiable at the origin. And then you can say, well, let's make it a little bit worse. And then you make it a little bit worse by going up, going down and back up. Oops, that's not what I wanted. So you go up and you put in another couple of trouble spots by saying I'm doing this and then I'm doing that and then I'm doing that, and I'm going to do that over here too. I'm putting in a couple more trouble spots and I'm going to go down, and then I'm putting in the trouble spots on the other side as well. So I'm going to change my graph to put in trouble spots. And now I keep doing that every time when I have a straight line over here. Then I'm going to replace that by a more jagged line. And I'm going to do that with all of the straight lines that I have in that graph. I'm going to replace all of them by more jagged lines. Then I've created more trouble points. And then I keep doing that. I keep messing up this function in this way. Keep messing it up this way. Then you create a function that actually turns out to be nowhere differentiable, because I will continue to mess up all these good parts by putting jagged parts in there. So there exists a function, there exists a continuous function if you want to on all of the real line on R, which is nowhere differentiable. So not only does a differentiable function, not only does a continuous function have to be, say that again. Not only can you make a continuous function that's not differentiable at a point, you can make one which is extremely non-differentiable because it's nowhere differentiable. Now look at some more examples. This one's a really interesting one. Look at the function f of x is x times the sine of 1 over x. That function is continuous at 0. But not differentiable at 0. The reason for it becomes visible if you try to draw the graph. So if you look at f at x is equal to x, and you draw that graph of f of x is x over here, and you draw the graph of f of x is minus x over here, then you will find out that x times sine 1 over x, depending on whether that sign is positive or negative, is going to sort of oscillate between those two lines. You look at that graph and the graph is going to do this. Investigate that a little bit. And on the other side it does the same thing. It goes back and forth between those two lines. When is it exactly on that line segment over here? Well, that's when the sine of 1 over x is equal to 1. When is it over there? When the sine of 1 over x is negative 1. And the same happens on the left side of 0. Now what you see is that at 0, those function values of x sine 1 over x get pinched into that corner over there. Same on the other corner. And that shows that that limit as x goes to 0 of x times sine 1 over x is actually equal to 0. Now how could you actually prove that? It's not hard. You would say, well, x sine 1 over x minus 0 in absolute value is the same as x sine 1 over x. That of course is less than or equal to absolute value of x times absolute value of sine 1 over x. And that is less than or equal to the absolute value of x. Now the fact that the limit as x goes to 0 of the absolute value of x is equal to 0, that converges to 0 as x goes to 0, gets you that the left hand side also has to converge to 0, and that means exactly that x sine 1 over x is continuous at 0. Now is x sine 1 over x differentiable? No, it's not. So f of x is x sine 1 over x is not differentiable at 0. How would you do that? Well, take a look. If you take the limit as x goes to 0 of x times sine 1 over x minus 0, and you divide it by x minus 0, then you actually get the limit as x goes to 0. X sine 1 over x divided by x is actually equal to the sine of 1 over x. And then you got to think, as x goes to 0, does the sine of 1 over x approach a number definitively? Well, no, because that sine of 1 over x will often be equal to 1. For instance, if x is equal to pi over 2, then the sine is equal. If x is equal to 1 over pi over 2, then the sine of 1 over x is equal to pi over 2, which is equal to 1. But that keeps happening. Okay? That's not just for pi over 2. The sine of 1 over x is equal to 1 whenever x is equal to pi over 2 plus 2n pi. So when x is pi over 2 plus 1 over 2n pi, then the sine of 1 over x is equal to 1. And that 1 over x is approaching 0 as n goes to infinity. On the other hand, the sine of 1 over x is equal to minus 1 whenever x is equal to minus pi over 2 plus 2n pi. So when you approach 0 in two different ways, then one time you're going to approach 1, and the other time you're going to approach minus 1. And that, of course, cannot happen. Now, this improves this negative behavior if you don't like that limit as x approaches 0 of sine 1 over x does not exist, and you call that a negative thing. This negative behavior improves with the function g of x is x squared sine 1 over x. Show that g is differentiable. At 0. And that's an easy exercise. That's actually easier to write down than the fact that that limit does not exist. Now, if we have introduced the derivative of a function, you very well see that you can also introduce the second derivative. That's the derivative of the derivative, if that derivative of the derivative indeed exists, or for that matter, an f with 3 primes. And if it gets to the 17th derivative, then we do no longer write 17 primes, but we actually write f17 with parentheses around it, meaning that I take the 17th derivative of the function f. Now there are exercises that I want you to work, and the exercises are page 163, exercises 1, 2, and 8. Now 1 and 2 are completely straightforward. 8 might give you some trouble, and if it does, we're going to talk about it next time. And that's all that I had in mind for today. So I have introduced the derivative. I figured out that if a function is differentiable, then it is continuous. And I did some relatively easy calculations with connecting continuity and differentiability and finding out functions that are continuous but nowhere differentiable. We're going to use that later this week to do even more spectacular things with the derivative and the second derivative. And I can't wait to have you then back in class. That time you have done these exercises, and I will again be there while you can actually see me. So this time I decided I'm writing this down for you to just read and listen to my voice. And then on Wednesday, we'll have again a live meeting. And that's also important so that you can then ask questions about the exercises that I sprinkled throughout this text. Thank you for paying attention. Email me at any time you have any questions about the material, and then we'll see each other again on Wednesday. Bye.